Hello, everyone. Hello, hello. Love talking. Hello, welcome to Hone, the best CTF category. All right, first, some announcements. We might play Dead Face CTF at 9 p.m. tomorrow. So if you're interested, react to the Discord message.
9 a.m. Sorry.
9 a.m. Sorry. And then also next Thursday's meeting, which is block picking, will be in MSCB 100, so not here. All right, the scoreboard, we have a few new people on the scoreboard, so yay. Everyone give them a round of applause. And here's the meeting flag, so I'll give you a couple of seconds to enter that in. It's just 8 A's, 8 B's, and 8 C's.
Isn't that 7 B's?
That is 7 B's.
Never mind. What'd you do, Sam?
Over.
It's supposed to be 8.
Yes.
Yeah.
Is it 8 in the thing or?
No, it's that.
Okay.
Oh,
So
it's supposed to be.
that's 878 in
It's
the
878.
Yeah.
Internally, I wanted it to be 888. I have screwed up monumentally.
It's okay.
We still have.
For real.
No, it's okay.
Okay. Okay, so what is PWN? A more descriptive term is binary exploitation, and it deals with how executables are compiled and how a CPU like actually understands the executable you compile. And this deals a lot with a lot more like lower level stuff. So like if you attended the assembly meeting from earlier this semester, that would be pretty useful. But also most modern exploits and like most valuable exploits, the ones that happen the most, deal with this kind of stuff. So it's pretty important and it's pretty cool, and you all should try to challenge it. But it's also really hard. So like don't be afraid to ask questions. I got to ask a bunch of questions when I was learning this stuff last year. So don't be afraid to ask questions. Okay, an overview of how the general memory of a program is. Basically, it's just a bunch of numbers, and they're organized like using addresses. And you can think of the way addresses work as just a giant array list where addresses are sort of like the index. And so the bytes in the program, they serve like one of two purposes. So first is like instructions. So think of back to the assembly meeting from earlier, like your functions are expressed as assembly instructions, and this area is where that data is stored for your executable to actually run. And then there's just data, which can be like basically anything, like a number, it can be a string, a character, or it can just hold another address that points to another number, string, or character, or it can be anything. And this is a general like memory layout. So like usually like your functions and like global variables instructions are stored at lower addresses, and then you have the stack at the very highest address, and the stack grows downward, as in like the addresses decrease when you go down. And so the ones that we care about today are the text section, which is the instructions, so like instructions for your functions, and then the stack, which is at the very, or I guess, top of memory. Yeah.
Okay, so let's talk about smashing the stack. The stack is laid out in machine words on 64-bit systems. So every time we add something to the stack, we're adding 8 bytes to the stack. So if we call a method with 3 variables, on average, those variables might be loaded onto the stack first. And then we're gonna place the return address, the saved frame pointer, and any local variables that the that the method creates onto the stack during execution. As we have an example here, we have two 8-byte buffers of characters. And so when we call this vulnerable function out of main, we're gonna put the return address, which will be at the end of main, onto our stack. The frame pointer, which is not entirely important at the moment, and then, and importantly, our local variables of stack R1, stack R2. And this is how the stack grows when you are calling functions and declaring variables within your code. So we have a function that is defined in C, and unfortunately, due to C's necessity to never deprecate anything ever, still exists. It's called gets or get string. Basically, you call it, and then it will get the string from the terminal input and place it into the buffer. The issue is this has no bounds checking whatsoever. If you send it 2,000 bytes, it will place 2,000 bytes into your buffer. If your buffer is 8 bytes, something will crash. People didn't realize that this was unsafe in the 90s, and that's how like things built up to more complicated exploits, and the damage was already done and the standard was set. So if we have our two 8-byte buffers and we call gets onto stack variable 2, what will happen to stack variable 1 when we print out when we overflow it? Well, we'll print out our extra bit of overflow. So here we're sending 8 bytes of the letter A and 8 bytes of the letter B, and then our program calls puts, which is just put string out to the terminal on stack variable 2, even though, or 1, sorry, stack variable 1, even though we never touched stack variable 1, it got overflowed. We've changed it, we've modified it. So as you can see, we'll fill it with A's, fill it with B's, and suddenly, we've changed what the program does with just 8 bytes of overflow. So now we need to talk about like that return address that we mentioned, because the return address tells our program where to go once we're done executing our function. If I have down here this puts call, we'll say that the instructions that starts this puts call is located at hex address like 1004. What gets saved onto the stack is that address 1004. So that will, when our vulnerable method returns, the instruction pointer will jump to that address and start, resuming the execution of code. But we mentioned that we can overwrite things on the stack with unsafe calls to gets. So if we have our win function, which might like print out the flag or do something that we want to happen, if we have it located at this address, which I'm not going to ramble out, if we have an overflow, we can actually fill it with unprintable bytes, because nothing is stopping us from piping the input to this program via some automation. We can pass in unprintable bytes and actually specify a specific return address to jump to. And suddenly we've made the program do something that it was not coded or designed to do. So this is the kind of basics to stack smashing and taking control of programs that you might encounter in the wild. There's also kind of a similar idea of integer overflows. In the same way that you might have an integer on the stack and you're able to overflow it, buffer overflow, you might also have the fact that integers are typed values and are interpreted as that type in assembly. So if I define, a 64-bit number, once I try to store a value larger than what it can represent, which is large, but too much to think about. I think this is actually a 32-bit example. Yeah, I should do a 31. It's going to wrap around and give you a negative number instead. So this is important because, if I index into arrays or do things like that, I can index backwards, which can be dangerous as well.
All right, now we'll talk about how to actually send your exploit after you figure out what you do. So first, we need to talk about something called endingness. You might have been a little bit confused with the stack smashing slides when we sent the return address, because it seemed like everything was backwards. Well, in x86-64 systems, the least significant byte is stored first in memory. So like if you were to express the number as like just a hexadecimal number, the last 2 digits of that number would be stored first, and then the last third, and like it would go backwards like that. You can see the example how it's stored like that. So that stuff's kind of confusing, but you'll see later that Hone Tools has some pretty good utilities for not having to worry about that. It'll just like pack it for you. Another thing is you might have wondered how like we would know where a function address is in order to overwrite the return address to that function. And you can do this in a couple ways. One is you can use something called object dump, and you can just grep for the name of the function, and it should tell you the address. You can also run the challenge in GDB and then just type info address main or iaddr main. And also you can just look in GitHub, but honestly the other 2 ways are probably better. Also, some of the bytes that you might want to send, you might not necessarily be able to just simply type in the program. So another way to send that exploit is to use echo with the -e flag, which allows you to escape some characters. So then you can send those like bytes that you can't normally type otherwise to to run your exploit. But yeah, refer to the slides if you need to. Okay, and then probably the most useful thing for your Pwn exploits is a library called Pwn Tools, which I believe we've talked about in some previous meetings, but you can install it with that command at the bottom. But Pwn Tools gives you a bunch of different things you can do to make your exploit development a lot easier. So if you see on the like challenges for SIGPwny, it'll have you netcat into a server. So like NC and then a host and then a port. So you can basically do the same thing in Pwn Tools by creating a remote object and specifying the host, which is child@sigpwny.com, and then a port number. And then you can just like the same way the program would output stuff as you ran it in your terminal, you can also take that output using commands like receive line, and then you can type stuff in the terminal using send line, and you can also, after, like if you want to see or interact with the program after you sent your exploit, you can use something called interactive to send stuff later. It'll basically just like allow you to interact with it as if you just ran the program or the program in the terminal. And this is a specific example for an exploit that overwrites the return address from win function that you want to call. So we can simply store the win address in a variable and then add some padding to our exploit, and then we can, like I said before, you don't really have to worry about endianness because Pwn Tools will default to little endian. So if you want to pack the address it as like a 64-bit integer for you to send, you can just use the p64 function, and then you can just send your exploit and then call interactive.
Okay, so one last thing I want to talk about. Those last 2 examples showed how to connect to a process that's being hosted by a server. You are completely welcome and should download the program itself and run it locally. You can do this by just saying process instead of remote. It will make the same type of object with the same interaction, all that good stuff. You can also attach GDB to these processes while Pwn Tools is interacting with it. This is extremely important if you don't know what your program is doing and it's crashing when you think it should be like returning to somewhere else or popping a shell or doing God knows what. So there are 2 ways to do this. You can start it at the dawn of time by calling gdb.debug. That will start GDB the moment you run the Python script. The other way is use GDB attached with the existing like connection object. This won't work if you have a remote connection, because GDB can't work on a process it doesn't have access to. Both of these require a terminal multiplexer, like TMUX. If you are on Windows, Windows Terminal also just supports this for some reason. I found this out recently. It also comes with a like nice local, not necessarily local, but you can pause your exploit to require you to like hit enter on Home Tools before it moves on if you need to like wait for things to happen. I've included on the slides, I'm not gonna read everything off here, kind of like a little cheat sheet. There are different functions for receiving and sending lines. They are very useful depending on what the program requires. Things that you might want to use a lot is receive until, which gives a specific delimiter, and send line after, which does the same thing, but then immediately sends the line. If your Pro Tools script halts with one of these calls, that means you haven't typed the delimiter correctly and it's still like waiting for it. One of the important things that will become like more prevalent as you do more complicated exploits, there's a class called ELF. You can say ELF and then provide a file or libc or something. And you can access the symbols and addresses from that file directly, like a dictionary. And additionally, if you're using TMUX, I like to split it vertically, so you can copy this line to cause TMUX to automatically split vertically when you're like starting GDB. Yeah, so next meetings. This Sunday we are, well, it has ruined everything.
No.
Oh, kidding. This Sunday, we're doing Pwn 2 with Kevin. I think you also might be presenting that as well. So watch out for Pwn 2 with Kevin and Akhil. Akhil.
Yeah.
Next Thursday will be lockpicking with Emma. It will be in MSEB 100 instead of here. So don't come here. Next Friday at 6 p.m. we have a workshop with Caesar Creek Software. We haven't determined the location, but please show up. They're cool people. Might get an internship. Talk to them. Challenges. We pulled the challenges from fall CTF up to the PWN category. So the stuff that you should be able to do from this meeting alone is the first like 3 PWN challenges in the sequence, which is 0, 1, and 2, like whatever I name them, and the integer overflow challenge. You can probably get away with a little bit of Googling to solve the execute challenge, and the format challenge might be a little tough to do, but we are welcome to help you with those as well if you get to them. Yeah, I think that's it. Yes, so meeting flag has been repasted. You didn't get it. Thank you everyone for coming. I think that's it.
Also, if you have a Mac and you can't run the binary or you can't debug it, raise your hand and I'll come talk to you. Okay. Yeah, Docker, but you still can't debug in Docker.